Why is it that the first 737 almost looks the same as the current 737? For reference, this is the first Porsche 911 launched in 1963, and this is their current model. With the 737, apart from the big engines and the winglets, there is not a lot of difference one could point out. The first passenger jet is considered to be the Boeing 707. Developed in the 50s, the nose section looks weirdly similar to that of today's newest and shiniest 737 MAX. Have they copied their 70-year-old design? Has that led to the recent catastrophic crashes of the 737 MAX? Partly and kinda. You see, the nose section in particular was obviously not a contributor to those crashes, but the reusing of the old design was. But more on that later. Have a closer look at the nose section of Boeing's first jet aircraft. The 707, 717 and 737 practically share the exact same cockpit or nose section with one another. The nose section is, apart from the wings, one of the more complex things to design on a jet aircraft. As we'll learn later, a well-designed nose section will cause less drag and therefore a better fuel efficiency. Boeing has copied part of the old designs and older aircraft and reused them in newer models. The best example is the Boeing 737. Boeing's first jet aircraft, the 707, had its nose section designated as Section 41 in the engineering drawings. It is a portion of the aircraft extending just aft of the cockpit windows to the very front. Therefore, the Boeing 707s, 727s and 737s have the same Section 41. The similarities among the jets are abundant, with only very minor changes made to the design to accommodate the different sized cabin behind the cockpit. As you probably know, the latest implementation of the 737 is the 737 MAX, with its original designs dating back a few decades. This is Boeing answering to Airbus's A320neo, while still using the same basic dimensions as the original Boeing 737. In fact, the width of the fuselage has remained the exact same over all generations of aircraft. So why is it that the basic dimensions and looks of the current 737 MAX model date back to Boeing's first jetliner, the 707? First off, it's an immense technological effort to design any aircraft, let alone a jet aircraft, with almost no prior knowledge and experience in that very field. That being said, with today's advancements in understanding of fluid dynamics and advanced simulations that just was not possible back in the 50s when the 707 was designed, wouldn't it be possible to design a fuselage way more streamlined and more efficient rather than just copying and reusing old designs? To understand why seemingly jets have not changed during the last 5 decades, we first have to understand how an aircraft is designed, but more specifically how a jet aircraft is designed. Prior to aircraft design, a clear purpose must be established. Commercial airliners are crafted with the aim of effectively transporting cargo or passengers over long distances, prioritizing fuel efficiency and stability. On the other hand, fighter jets are specifically engineered for high-speed maneuverability and close ground troop support. Modern passenger jets are engineered to maintain a comfortable cruising speed of approximately 450 knots at altitudes ranging from 32,000 to 42,000 feet, ensuring both efficiency and weather avoidance. They prioritize passenger comfort with pressurized and air-conditioned cabins and are designed to take off and land on runways of varying length, ranging anywhere from 1,500 to 4,000 meters under different temperature conditions, even in the event of an engine failure. That's right, a modern commercial jet aircraft has to be able to take off with one engine at every takeoff. Subscribe to my channel to not miss the future video about engine failures coming soon. Compliance with regulatory standards like FAA or EASA, such as the requirement to evacuate the aircraft within 90 seconds with half of the exits blocked, is essential as well. Additionally, airports may impose restrictions like a maximum wingspan of 80 meters to prevent taxiing collisions. These and many more factors collectively define the objectives of a modern jetliner. Initially, the design concept typically takes shape as a rough sketch considering environmental constraints such as cabin dimensions, passenger capacity, wingspan restrictions, and the smallest airports where the aircraft is intended to operate. In the past, design teams were rather small and led by a single chief engineer who oversaw everything. But as time went on, military and airline aircraft became more complex. Nowadays, large-scale projects involve multiple teams from all over the world handling different aspects of the design. In the early days of aircraft design, Engineers primarily relied on analytic theory for their engineering calculations and conducted a substantial amount of experimentation. These calculations were both labor-intensive and time-consuming. In the 1940s, some engineers sought ways to automate and simplify these calculations. Despite these simplifications, the calculations still remained extensive. The advent of computers, however, opened up new capabilities to automate those calculations. Nevertheless, the absence of effective design visualization tools in the early days and the need for extensive experimentation due to a lack of simulations held back progress in aircraft design. The emergence of programming languages allowed the engineers to create customized programs for aircraft design, initially on mainframe computers, utilizing low-level programming languages that required users to have a deep understanding of the language and computer architecture. The subsequent introduction of personal computers marked a shift towards a more user-friendly and visually representative design programs in use today. The aerodynamic objectives. Aerodynamically speaking, an aircraft should carry a payload with the least amount of drag and a sufficient amount of lift. The lift require changes with the amount of speed, hence the wings have to produce more lift during slower flight as less air is being pushed over the wing. That's what slats, flaps, and angle of attack is there for. Let's begin from the outset. Drag comes in two primary forms: induced drag and parasite drag. Induced drag is a result of generating lift, while parasite drag is akin to the resistance you feel when sticking your hand out the window while driving at 60 miles per hour. Parasite drag will rise with the square of the speed. Half the speed will mean a quarter of the parasite drag. Parasite drag will also reduce when reducing the frontal surface. For obvious reasons, altering the frontal surface of an aircraft is challenging, as it must adhere to specific cabin width and height requirements to accommodate the payload or passengers. However, it is possible to modify in shape the frontal surface, the nose of an aircraft, and the tail, as the tail is very important as well. Looking at those four objects and the different amounts of disturbance they cause, it is easy to see why an aircraft looks a certain way. Those shapes can obviously not be used for aircraft designs, as a nose section, for instance, has to accommodate pilots, instruments, windows, weather radar, nose wheels, and other miscellaneous equipment. And if you wondered why the nose is not pointed like an arrow, the blunt or round nose design features a smaller surface area when compared to sharp, elongated noses, resulting in reduced skin friction drag. Experiments have demonstrated that in subsonic flight, round noses generate the least amount of drag. Concerning the wing design, this is way too complicated to go into today and would call for a completely separate video. But general obvious design features like the swept back wings benefit the aircraft by reducing drag at high speeds and increasing the critical Mach number. Important to note, the Boeing 707 did not employ a supercritical wing design. Supercritical wings developed later gained prominence in the 1970s and 1980s to enhance transonic and high subsonic performance. Why haven't designs changed more substantially? As we previously discussed, designing any kind of aircraft, let alone a jet aircraft, commercially used, is a massive feat of engineering, designing, testing, and certification. Looking at Boeing being constantly in the business for over 100 years now, we might be able to answer the question. Boeing has a long-standing philosophy that remains true even today: don't fix what isn't broken. Continuity in design. Boeing aimed to preserve design continuity and draw upon the knowledge and expertise acquired during the development and successful operation of the Boeing 707 by retraining shared design elements such as the nose section that could capitalize on established design principles. Cost efficiency. Employing a similar nose section design allowed Boeing to recycle parts, manufacturing procedures, and tooling. This kind of parts commonality streamlines production and reduces costs. Customer familiarity. Airlines already operating the 707s might have found it advantageous to embrace the new 737. Common design elements facilitate the transition to a new aircraft model, potentially reducing training and maintenance expenses when multiple aircrafts in a fleet share similarities. To sum it up, Boeing went with the proven design for continuity, cost efficiency, customer familiarity, and obviously to shortcut the design process. How does the old 737 design compare to modern aircraft? The 737 MAX compared to the Airbus A320, the 737 biggest rival, actually has better performance numbers. In some regards, that is. It's a little bit faster and can fly a little bit higher. The range and passenger capacity are almost the same depending on if you compare the Max 7 or the Max 8. Only once you start to compare the bigger variants of each Boeing and Airbus, you start to see the noticeable difference, highlighting the disadvantages Boeing has with its old design. The 737 was designed in the 50s and 60s with a low wing height to improve ground handling and reduce the need for tall jet bridges and specialized ground equipment at airports. Because it technically is almost impossible to increase the height of the aircraft without fully redesigning part of the wings and fuselage, the engine size is quite limited by the height above ground. Also, during rotation, a longer aircraft will potentially have a higher possibility for a tail strike. That's why the higher height of the Airbus is advantageous. They can grow in size more easily and fit big engines on the wings without any problems. I strongly believe that the 737 MAX, as it stands today, represents the culmination of the 737 series, as it just becomes increasingly challenged to meet evolving demands of today's airlines with an aircraft design that has originated over 5 decades ago. It's expensive to build a plane, but more expensive to design a new one. Throughout the whole history of aviation, you will find similarities and commonalities from one aircraft type to another aircraft type, with even old ones with the design dating back several decades. We've talked a lot about Boeing in this video because of its immense legacy dating back 100 years. But Airbus essentially does the same thing. The cockpit of the A320 developed in the 80s is found with some minor modifications on the A330 and A340. The new A350 and A380 aircraft have a more newer generation of flight decks with some updated screen and a more comfortable pilot aircraft interface. But again, many switches, buttons, system architecture, and logic and flight characteristics are actively copied from their older brothers, the A320. Now, for one, to save costs during the design process, but more importantly, to ensure commonality among aircraft types so as to ease the transition from one aircraft to another during flight training. For an A320 pilot to transition to an A350, it only takes about 11 days of theory and practical training. And for any plane manufacturer, this remains true. Plane makers even copy each other's philosophies and general design elements to have a make-wide commonality among aircrafts. This includes general design elements of the primary flight display or the layout of the autopilot control panel, holding true to the philosophy, don't fix what isn't broken. Many often overlook the fact that, unlike a car, an aircraft must undergo an extensive testing and certification process that can span several years. This is why any release of any new aircraft is exciting, in stark contrast to the introduction of Kia's 2024's lineup. Anyway, has the passenger jet actually improved over the last 6 decades? While it might not look like much from the outside, as general design and appearance have been kept constant over the years, we have seen tremendous improvements in efficiency, safety, comfort, and environmental impact over the last 20 and 30 years. Not only because of stringent international safety and performance standards, such as those set by the organizations like FAA and EASA, but also because of the competitive nature of the aviation industry that encourages manufacturers to push the boundaries of innovation, striving to create a more efficient and appealing aircraft to meet the demands of airlines and passengers. So what has been changed? If we take a second to just look at the overall appearance of a modern aircraft, we see a few minor improvements in design that have a tremendous impact on overall efficiency, with the numbers getting close to 50% of improvements from the first 737 variants to now the 737 MAX. Again, comparing Boeing because Boeing has such a vast legacy of aircrafts dating back several decades. The wing has seen dramatic improvements even over recent generations of aircraft. The aspect ratio of the wings, which refers to the ratio of its wingspan to its mean chord average width, has increased with newer aircraft. The wingspan has gotten so big that the newest Boeing 777X will fold up its wingtips to be more easily accommodable on airports. This will lead to a reduced wingspan of 67.4 meters from its normal in-flight 71.6 meters. Additionally to the higher aspect ratio, the wing has also gotten thinner and has seen some advancements in shaping. Especially the wingtips now in a way resemble that of a bird. On the 787 you can see the wing at work, which just looks beautiful. Also, advanced leading edge and trailing edge high lift devices, flaps and slats, have come a long way. It would look like a barn door from the oldies hanging there below the wing has now a complicated and highly advanced mechanism that not only increases the downward force of the trailing edge, but also the general wing area and airspeed on top of the aerofoil. The fuselage, and with that especially the nose section of the aircraft, has become more streamlined across all major aircraft manufacturers. Either the Embraer E-Jet series, the former C series, now A220, the 707, or even the A350 have all become more streamlined, with some of them even implementing curved windscreens, which makes them even more efficient and seamless. The engines are probably the biggest difference that anyone could point out. The first engines were traditional jet engines, very similar to those in a fighter jet, although without afterburners. Today's jet engine feature a big fan similar to a propeller in a turboprop, which produces the majority of the thrust. Those new engine models have a bypass ratio of up to 12:1, meaning 12 parts of cold air are accelerated by the fan only, and 1 part of hot air goes through the engine core. That's why engines are getting so much bigger, and that's why the old designs of the 737 might have reached the end of time with the 737 MAX, because there simply is not enough space below the wings to fit any bigger engines. The aircraft systems have been completely reinvented. Not only are most modern jets fly-by-wire, meaning traditional mechanical linkages are replaced with electronic cables, allowing pilots to control the aircraft through computer-mediated inputs. Everything is controlled by a computer with a sort of a control logic behind it. Every little system. With the 707, a flight engineer sat behind the pilot, controlling primarily the engines, but also most of the other systems. Today, the FADEC, or Full Authority Digital Engine Control Unit, will control and manipulate and check over 1,000 parameters each second to ensure peak engine performance at every phase of flight. And that engine data is actually transmitted to maintenance facility to find out about any exceedances and abnormalities of parameters before a potential failure can happen. The autopilot has become so advanced that it can land the aircraft without pilot inputs and stop on the runway. So there has been quite a good amount of significant improvements over the last decades, just that to the untrained eye, most of them are not immediately apparent. What improvements can you think of? Tell me in the comments down below. Are old aircraft designs unsafe? Older aircraft designs like the 737 may be ever harder to improve with advancements in regulations and requirements proposed by operators and regulators. The lack of a crew alerting system in the most recent 737 MAX 10 model is the ultimate reason why it is still lacking a certification by the FAA. Even the Diamond DA40 that I fly with friends on a regular basis has that system. It's a general aviation aircraft and looks like this. Aircraft crew alerting systems play a pivotal role in ensuring safety by providing essential information and timely alerts to the flight crew regarding the aircraft systems and potential issues. The system keeps the crew well informed and enables them to respond promptly and with precision to any arising problems. So yes, a modern jetliner will make a pilot's job easier with identifying a problem or even managing a problem. But pilots are trying to handle any malfunction that could arise. And even in those old dinosaurs 737 flight decks, pilots can obviously manage any malfunction. The ultimate reason why passenger aircraft have been in service for such a long time comes down to the expensive development and certification process that any commercial airplane has to go through. Changing a fundamental design is often not feasible, as today's manufacturers are under an immense pressure by competitors and potential clients. The development of the 737 MAX was necessitated during a period when designing an entirely new aircraft was not feasible. The A320neo just came out, with Boeing operating airlines around the world eagerly waiting to finally update their NG models. So Boeing acted fast, answering with the MAX. The aging airframe design with its low-hanging engines ultimately led to the requirement of the MCAS, Maneuvering Characteristics and Augmentation System, which was part of the reason why 2 MAX aircraft crashed, leading to a death of 346 people. All of the 737 MAX aircraft were grounded back then and then renamed, but it also received a software update, now utilizing 2 angle of attack sensors instead of 1, to feed the MCAS system. Pilots also received some more hands-on and in-depth training regarding the system, helping to handle a failure. Safety is of the highest priority. Economic feasibility is of the second highest priority, and that sometimes means flying an aircraft fundamentally designed in the 50s and modernized this decade today. Until the next one, stay safe.